So part C is asking us to draw the Amperian loop that would give us the field at point P. So the proton moving in this direction, the appropriate Amperian loop is something that would be symmetrical around the area of interest, in this case the path of the proton, and would also include in somehow the point P. So in this case we're going to make our Amperian loop something like this, a circle. So if we were looking at the path of the electron moving that way, so this is a side view, the Amperian loop would be a circle that is going around the path of the proton and intersects at the point P. And the intersection at point P will be useful for the integration that we are about to do. So part D asks to find the electric flux through the Amperian loop. So the electric flux equals the integral of the electric field dotted with dA. Well, the dot product is just looking at the magnitude of the two components that are perpendicular to each other. So we can take the dot product out and multiply that by cosine of theta. So looking here at the diagram that we have something like this. The horizontal distance is going to be vt, the velocity of the particle, times the time it has been traveling for. Its vertical distance will be y, and then we'll call the distance from the proton to a point on that loop, somewhere on that loop, is going to be r. This is helpful in that the electric field is defined as k times q over r squared, k being the constant, q being the charge, r being the distance from the 2 points. dA, so because we have a disk, a useful shape that we can integrate over would be a ring. So it would be something, a smaller ring, an infinite amount of rings of varying radius. So when we have a ring of a very small radius, the area of that ring is going to be the circumference, so 2 pi y, in this case because we are calling our radius of the circle is the variable y. So 2 pi r, which is 2 pi y, times the width of the ring, times dy. Cosine of theta, if this is our angle theta, the angle between the area vector and the electric field, cosine of theta can be rewritten as v times t, or vt over r, not v times t, vt over r, because that is the adjacent side times over the hypotenuse. So using these three rewritten forms, we can use that back in our equation for the flux. So E being kq over r, so r is going to be, if we look at the right triangle here of vt, y, and r is simply going to be the magnitude of vt squared plus the magnitude of y squared and the square root of all that. So r equals the square root of vt plus y squared. And we can rewrite that here in the electric field. So r squared gets rid of the square root and we get vt squared plus y squared. The dA, with simple substitution back into the formula, and then cosine of theta, vt, and again we'll make the same substitution for r being the square root of vt squared plus y squared. So I'm going to rewrite this again, which is going to be 2 pi kq vt times y dy over, our denominators are the same number, so we can combine those and add the exponents, which gives us vt squared plus y squared to the 3/2. And we're taking the integral of that, remember, to find the flux from the definition of the electric flux. Everything, almost everything, in the numerator is a constant, so we'll take those out. 2 pi kq vt, and we will leave everything with a y term in it. So in this case, the y dy over vt squared plus y squared to the 3/2. The integral of this, of a constant squared plus the variable squared with the variable on top, dy, is defined as, so this integral, the whole integral, can be 1 over the square root of y squared plus vt squared. So that is the definition of that integral. I'm going to rewrite this using that substitution for the integral. So that equals 2 pi kq vt times 1 over y squared plus vt squared, square root of all of that. So adding that all together to find our electric flux, which is what this problem is, this part of the problem is asking for, we get that the electric flux equals 2 pi kq vt over the square root of y squared plus vt squared. And this is the answer that we will use in the next part, part E.